Since Sputnik 1 was launched in 1957, all spacecraft which have orbited the Earth have been placed there by expendable rockets. Conventional rockets, whether solid or liquid propellant, have a fundamental design flaw. A large proportion of their takeoff mass is taken up by the oxidizer required to allow combustion to take place. The irony is that for much of their flight, the rocket is passing through all of the oxygen it needs in the Earth's atmosphere. Reaction engine Skylon concept uses a unique air-breathing rocket engine, which has the potential to revolutionise the process of achieving orbit. Skylon aims to make the delivery and recovery of payloads to and from orbit a routine airliner-type operation. Passenger modules could be inserted into the vehicle's payload bay for ferrying astronauts to and from orbit. The Skylon concept and its revolutionary air-breathing rocket engine has spent over 3 decades in development.
I began sort of thinking about single stage to orbit back in the 1970s when I was at Rolls-Royce, and rocket engines just aren't good enough. There are lots of variations on rocket engines, so rockets which use 3 propellants, liquid oxygen, hydrogen and kerosene, so that you can optimise the engine. None of these things quite hack it, and in 1982 I started to have a look at the possibility of actually getting the oxidizer from the atmosphere. People had looked at liquid air cycle engines and things like that, but what I looked at was not cooling the air to liquid, but just cooling it, so very cold gas, then looking at the work required to compress it, a little bit of clever thermodynamics, and the engines that formed the basis for HOTL came out of that. And so during the 1980s, thanks to input from Bob Parkinson and John Scott, Bob from the British Aerospace side of things, John Scott from Rolls-Royce, we had a good run, and latter part of the 1980s we formed the HOTL project. British Aerospace led that, and we had the opportunity to look at a very, very different way of getting into orbit. It's a bit of a mixed result in that technically it looks as though it should work. When we put all the practical things in of a real aeroplane, it fell short. Now the HOTL project came to an end, the government decided not to support it, the companies sort of pulled out of it, and John Scott, Richard Varville and myself, we created reaction engines in order to rescue all that technology. The real problem that we'd met on HOTL was that the aerodynamic centre moves forward. The lift, as you go up the Mach number range, the lift on the wings falls off, but the lift on the large hydrogen tank forebody remains constant, so the lift moves forward. The centre of gravity on HOTL stayed pretty much where it was, and therefore you get a huge moment, 2,000 ton-metres, that had to be taken out. The step that we made was a rather obvious one, which was to put the engines on the wings rather than on the back of the aeroplane, and then wherever you put the wing, the centre of gravity went with it. The second thing that we did was chop the hydrogen tank in half, and we burned the hydrogen during the air breathing part of the ascent from the rear tank, so as the centre of pressure still moves forward but not so much, the centre of gravity now also moves forward, so we managed to keep the two in place. So the main changes that you see is that the engines have gone onto the wings in order to give us control of the centre of gravity. We've chopped the hydrogen tank in two, and so it becomes long and spindly. So HOTL looks sort of rather dumpy with the engines on the rear, and Skylon looks sort of rather sleek and slender with the engines on the wingtip. So it's not so different when you actually look at how it came about. The principles behind the SABER engine are very simple. We had to make use of the lower atmosphere, and jet engines do that all the time, of course. But once you're up to about 2.7, 2.8 times the speed of sound, a jet engine's finding it very difficult to cope with the high temperature air that is going in. But if we've got a vehicle which has got liquid hydrogen on it, then the liquid hydrogen is very cold. It's also capable of absorbing 3.5 times as much heat as water for the same temperature rise. So you've effectively got a very good coolant in the fuel. So the answer is try to use the fuel to cool the air entering the engine so that you can get to a bit higher Mach number. You'd like to get up to around about 5 times the speed of sound instead of about 2.7 or so. And that looks possible. People had looked at this before, but what they had run into the problem is that the amount of liquid hydrogen you need is very large, about 4 times as much as you need just for combustion. So essentially the liquid hydrogen's become a coolant, you're just throwing it over the side. What I found is that if you're a little bit cleverer with the thermodynamics and you don't just use the hydrogen to cool the air, but you use some of the heat out of the air to actually drive the engine, then you can halve that astronomical amount of liquid hydrogen, and that's just enough to make all the trick work. So whereas on the original concepts that were explored in the 1960s, it doesn't quite hack it, once you put the slightly more sophisticated thermodynamics in, you find that everything just about comes together. You've still got to be very careful. You've got to make sure you get everything right, the size of the aeroplane, the size of the wing, the thrust of the engines and so on. But once you've made that change, it does work. The air enters the engine and is slowed down in the intake. So although the air coming in at Mach 5, it goes through the engine at really very low Mach numbers, and in some places very, very low. But when you slow the air down, of course, all that kinetic energy gets turned into heat, so the temperature of the air shoots up to about 1,000 degrees centigrade. So the first thing that happens is the air passes through the precooler, which is cooled by very cold helium, and it's been made very cold because further on in the cycle the liquid hydrogen fuel cools the helium. So cold helium, cold high pressure helium, cools the air going in, and within about a hundredth of a second, less than a hundredth of a second, the temperature of the air has gone from 1,000 degrees centigrade down to minus 140 degrees centigrade. Now when you've got very cold air, it's easy to compress. You squeeze it, it doesn't take too much power, the temperature goes up, so your next step is it goes into the compressor, it's compressed, it leaves the compressor at about 450 degrees C, typical of a normal sort of jet engine, but at very high pressure. At that point the pressure's gone up from sort of 1 atmosphere up to about 140 atmospheres. And at 140 atmospheres we can then push that into a conventional rocket engine. And we also push the fuel into the same rocket engine. So the rocket combustion chamber at this point in time is burning compressed air and ordinary hydrogen. Later on, of course, we turn off the air supply and just supply liquid oxygen, so that that rocket engine is now a normal rocket engine. On the helium side, the helium, of course, having cooled the air, is now hot, and it's at high pressure. So that helium goes through the turbine that drives the compressor. The exit helium then passes back through a heat exchanger, which is cooled by the liquid hydrogen. So it's now not such high pressure helium, and it's cold. We can now compress that helium back to high pressure, which is still cold because it, having been cooled by the liquid hydrogen, it's down at sort of minus 240 degrees centigrade. When we've compressed it, it's still down at minus 150 centigrade. So it can go back into the heat exchanger to cool the incoming air. So it sounds complicated, as do all engine cycles when you look at it, but the thermodynamics is actually very simple. Now, although I say the thermodynamics is very simple, it's taken us 20 years to get to the point where we actually understand what all the thermodynamic implications of these engines are. And it would appear that if you're only interested in getting up to 5 times the speed of sound, there are a lot of applications for this type of engine on the planet.
Rapid intercontinental transport is one such application. Reaction Engine's LAPCAT project is studying the concept of an air-breathing, hydrogen-powered hypersonic aircraft capable of cutting transit times between Europe and the Far East to under 4 hours. However, the precooler technology, which makes Skylon and LAPCAT feasible, has been a difficult one to master.
Putting a precooler in front of the engine's 2 major problems. First of all, for the SABER 3 engine and Skylon C1, each precooler is a 400 megawatt precooler. Now, if that was part of a nuclear power station, that would weigh 200 tons. So the very first problem you've got is to have a look at what all the parameters are and see if you can shrink all of that. And the answer is you can. So the 400 megawatt precooler in the SABER engine weighs about 1.25 tons, so that's the first major breakthrough. But of course, as the air is cooled down to minus 140, all the water vapor that's in the air, it's quite humid in this room at the moment, all of that freezes out. And as soon as we started doing the testing, we found that 3 to 5 seconds, the heat exchange is absolutely solid. It is frozen up. So a major step was to design a mechanism which would stop that frost formation blocking the precooler. Now, I can't tell you what that mechanism is. It took us a long time to devise it, and lots of other people have tried unsuccessfully. But our major breakthrough was to come up with a means of preventing that successfully, which could run indefinitely, so the precooler remains completely clear of frost throughout its operation.
Skylon is radically different in shape from all previous blunt body re-entry vehicles. How does it achieve this?
It's very interesting that all the textbooks indicate that re-entry has to be done with blunt bodies and large flat surfaces and everything tucked inside the shockwaves and so on. But it's quite clear that a vehicle that has to ascend to orbit in the first place has got to be sleek and sort of very low drag and so on. And so there appears to be a sort of contradiction. We went back to a sort of clean sheet of paper and had a look at all of these constraints, and what we found was that with the exception of a very few areas on the vehicle, the re-entry didn't look at all as the textbook said. We checked that ourselves. We then got a company called Fluid Gravity Engineering to do some calculations, and they essentially confirmed what we had found. Talking to a lot of the old timers in the UK who had been working at Farnborough back in the sort of 50s and 60s on hypersonic vehicles, they also reiterated that the problems do not appear to be as bad as the textbooks indicate. And then finally, only in the last year, we had DLR in Germany carry out some very sophisticated re-entry calculations for us on some of the best software going. And indeed, even the areas that we thought were bad turn out to not be very bad at all with regard to heating. So one of the things that is clear is that at some stage we're going to have to rewrite the hypersonic re-entry textbooks, because it is possible to get Skylon back into the atmosphere. In fact, not only possible, appears to be relatively easy. And then because of the actual low density of the vehicle, because we've got all the hydrogen tanks on it, it's typically 8 to 10 kilometers higher than the space shuttle at a given velocity. So we don't need those incredibly delicate tiles that the space shuttle needed to protect it during re-entry. So a large part of the design of Skylon is all about the thermal management and materials for the aeroshell and so on. All of that appears to be well within current and available technology. In some areas you get up to maybe a megawatt per square meter in terms of heat transfer rates. But in rocket engines and jet engines, we're typically used to dealing with 10 to 100 times of that. So we would probably carry a few kilograms of water to cool some of those active areas, which simply gets bled over the side of the vehicle. The foreplanes, for example, we carry about 100 kilograms of water to cool the foreplanes. We're still looking at what's the optimum way to cool some of the hot areas on the wing leading edge, but it probably only amounts to about another 50 kilograms of water to cool that during re-entry. Now obviously we've got to remember to fill the water tanks when the vehicle takes off, but given that's a procedure that we'll be on top of, then it does look as though that's completely manageable. We've broken the whole SABER system down into several areas, and so the biggest and most obvious one is the testing of the precooler, and we're coming up to the point we set up a pilot plant in Abingdon in Oxfordshire. We've got a number of extremely skilled people there. We can now build the heat exchanger components on a regular basis. It's taken quite a long time. It's been the lion's share of money that we've spent to the present time. But we've now got pretty much all of the components needed, and we're starting assembly of the precooler. Right now we've just done the preliminary assembly tests. That all seems to go together quite well, so that during November we're going to be actually building the precooler. At the end of November that will go up to our test site, which we call B9 on the Culham Science Park and just outside Abingdon, and that will go in front of a Viper jet engine ready to go into testing and demonstration in the first couple of months of 2012. Other work that we've done and completed is the cooling of the main combustion chamber. Because we use all the liquid hydrogen in the thermodynamic cycle, we have to cool the main combustion system with air and liquid oxygen. We've had DLR and Astrium in Germany actually do that work for us. That program's completed satisfactorily. All our design information's proved to be correct on that. We've also done work on nozzles. You've possibly seen the stern engines firing, and also lately the strict engine firing, and they are nozzles which are designed to be very specifically stable through the whole of the ascent to orbit, but also possibly to nozzles which will compensate to some extent for the back pressure losses which are typical on rocket engines. So that's all been completed satisfactorily as well. For the vehicle itself, as opposed to the engine, we've got technology programs going on the structure and the aeroshell, which are again going well. So there's a whole swathe of technologies that we're trying to address. Now, our ambition is that in about the next 12 months we'll begin a program which is cryptically called Phase 3, and within that program we will be building a completely self-sustaining engine, which is not a big engine, it's a very small engine, which actually makes it difficult, but that engine will demonstrate the thermodynamics of the cycle once and for all to all doubters, and there are still one or two of those out there. Thanks to the UK Space Agency and through them the European Space Agency, we had a very comprehensive review of the whole of the technology during 2010. And as a consequence of that, we're now getting quite a lot of interest from Europe, from Russia, from America, and other sort of Far Eastern countries. So I think that we've turned some sort of corner, but our main concern now is to make sure that the program goes ahead in Europe, and that we have not excited too much interest from the Americans. We wouldn't like to sort of see that we now lose this, having taken a long time to get the interest. It would be ironic if we now lost it because other people have taken more interest in it than the Europeans. I don't think we're going to sort of see an enlightened government, but we may see a lot of private investment go into the project. We're running on over 85% private investment, and that's been a total bill up till now of some somewhat over 10 million has gone in since 2004, and which is peanuts, but nonetheless has addressed major areas. If somebody gave us a blank cheque, then it would take us about 9.5 years to get to the point where we were producing production vehicles. Now, our business model is not make 3 vehicles and fly all the world's spacecraft. It's more like an aircraft model. What we want to do is to produce 30, 40 vehicles and sell them to competing operators. At the present time, the traffic to orbit is sufficient to support that level of competition, and one would hope that the costs would be so low that the traffic to orbit would now grow, and governments could then focus on doing those things which are not commercial, such as exploration of Mars, return to the Moon, and so on. And the transport could be supplied by commercial companies at a fraction, tiny fraction of the cost that it takes at the present time. Clearly, what we're trying to do is to break the von Perke paradox and get the bit into low Earth orbit cheap and easy. Von Perke pointed out that, ironically, to go anywhere in the universe, the bit into low Earth orbit is the difficult bit. Once we've done that, then missions to Mars, missions to the Moon, geostationary missions, much more of the same that we do at the present time, but more cost effective, is very important. Now, in order that we've got the design of Skylon right, and at this point in time, not for any other reason, it's interesting, but that's not our motive, We've looked at, for example, our Troy mission, which is a mission to Mars. We looked at how Skylon would enable 3 vehicles, a Columbus-type mission, each vehicle with 6 astronauts to actually go to Mars. We chose the manned flight for sort of 2028, but with a precursor mission that puts all the kit in the Martian orbit and down on the Martian surface 2 years early, 2026. And it turns out that Skylon is not really driven by that. Skylon could enable a mission like that, but isn't really driven by it. The geostationary mission, where we need an upper stage, so we've looked at a Skylon upper stage to go into the payload bay with a geostationary payload. That looks like that is really the design mission. That seems to drive everything else. And in this particular instance, if you're a bit cunning and choose the orbits right, Skylon carries out 7 orbits in low orbit, while the upper stage goes up to the higher orbit, leaves the payload, and then comes back just in time to meet the Skylon coming round on its 7th orbit. So Skylon can then pick up the upper stage and bring it back. Completely reusable system. In addition, if you're operating from a manned space station, for example, we looked at a rather larger vehicle that Skylon would carry into orbit in 2 halves, which we call the Flute stage, which is named after a Dutch transport barge. And the Flute stage would be able to transfer a 15-ton payload into geostationary orbit and then return to the space station reusably, or do the same thing out to the moon. Now, what we've looked at particularly is rendezvous and docking techniques so that the whole system is reusable. It's a system where you put hardware into orbit, and that hardware can be used 10, 20, 30 times before you then have to scrap it. And we think that in terms of cislunar space and missions to the planets, we could completely change the economics of that. I like to sort of cite Antarctica at this point in any discussion. Antarctica is further away than space. It's 8,000 miles compared with 100. Antarctica is an absolutely terrible environment in terms of weather and so on. Space is usually quite predictable, except for the odd solar flare. And yet operations in Antarctica are so cheap, I do not ever remember a government debate as to whether or not we can afford to maintain our interests in Antarctica. And that's because when a piece of kit fails in Antarctica, you put a new piece on an aeroplane and the next Hercules takes it out there. My view is that Skylon will make space like Antarctica, in which the bit into low Earth orbit will no longer be a political issue. We will just take our place along with everybody else. And as Bob Parkinson has often said to me, he would like space to be boring, and I think that Skylon, paradoxically enough, will be able to make space boring. I think if you go back and have a look at the sort of magnificent age of space, which I go back to the sort of Viking sounding rocket as part of the real start of the space age, where we learned how to lob a few things very high out of the atmosphere, in some cases extremely high, and then into orbit, and then of course the magnificent part of the exploration, the establishment of communications satellites, the use of space as a military tool for sort of stopping further military conflicts. We all lived through what sometimes were quite terrifying times, but nonetheless the strategy worked. So that has been good. But because of the dependence on ballistic missile technology, it was obvious that sooner or later it was going to go into a blind alley that it couldn't get out of. And I think that the industry, particularly the launcher industry, whilst it's done magnificent things, has just not seen this coming, has not prepared for it, has been very greedy in the sense that it just wants to turn out expendable launch vehicles. And I think that the UK, I mean, we can have a debate about what should UK governments have done and so on. And I think all of us would probably say we should have done more. But it has left us in a unique position in that we do not have any vested interest in any other means of getting into space. And so I think I'm depressed that the Americans can't get their act together, that all that the Europeans can propose is more of the same with regard to expendable launchers. But I'm quite buoyed up by the fact that maybe at this point in time, when the financial services industry is sort of down on its knees, and the government is saying that it wants high tech, and we may just have got to the right point at the right time for a change.